All right, so for bell work today, we're doing the same thing we did on Friday's notes. So very similar concept. On Friday, we talked about two things, dot products and then how to find the angle between two things. Okay, and they really tie together. So here in bell work, we're just doing that exact process. We're finding the dot product V times W and then working from there. Okay, so V times W, I hate when they write it like this. So I'm going to go ahead and write out that in vector form, 3 comma negative 1. And W is going to be equal to 2 comma 5. We are trying to find the dot product for part A. Part A is saying find V times W. If I want to find a dot product here, Evelyn, what am I going to do to find a dot product? Multiply my two x's. So I take 3 times 2, I get 6. Then what? Yep, and then we find the product of the y, so negative 1 and 5. And then we are going to add those two together, so it's 6 plus negative 5. My dot product is 1. Everybody go with dot product. The next thing we're doing, part B, is we are going to find the angle between V and W. I think you can do these in whatever order you want here, but we're going to do this next. Angle between V and W. So remember, we learned this formula on Friday. I will give you this formula on the test. I don't need you to be an expert. But there is my formula. Okay, so if I'm plugging in here, I know what V times W is, so it's going to be cosine of theta equals V times W on top. So that's my dot product. And then on bottom, I need the two, what does that mean again? Magnitude. I'm finding the magnitude of V, and I'm going to find the magnitude of W. If I want to find the magnitude of V here, Aaron, what do I need to do to find the magnitude of V? Pythagorean theorem, good. So she's doing Pythagorean theorem here. So 3 squared plus 1 squared. That's 4, or 9 plus 1, it's 10. And then you got to take the square root of it. So it's square root of 10. My other one, same thing with W here. 2 squared plus 5 squared. That is going to get me 4 plus 5, that's 29. We got to square root that. Cool. Those are my two magnitudes. I get that. I get that. That's my setup. What else do I need to do here to get rid of cosine? Inverse cosine. So you're doing inverse cosine of that whole mess. All right. And plugging this into your calculator, if you're not plugging this into your calculator, you're going to make a mistake. Make sure you're in degrees, because of this chapter, we are going to be in degrees the whole time. Okay. I'm doing second cosine. And then I would strongly suggest you doing it this way. One of my smartest kids last period was struggling. Hey, I keep getting an error. It's because you're not typing it in the correct way. We want to type this in as a fraction. Okay, alpha F1. If not, on bottom, you've got to put that whole thing inside of parentheses, which you can handle as well. You're just more likely to make a mistake. So on top, it's a 1 on top. On bottom, it is root 10 times root 29. Okay, if you're not typing it in as a fraction, that whole denominator needs to be in parentheses. 1 divided by root 10 times root 29. I type that in. I hit enter. Boom, there is my answer, 86.634. So theta equals 86.634. Everybody with me to that point? Are they vectors parallel, orthogonal, or neither? Neither. That one's pretty easy. It's 86 degrees. That is not parallel. That's not orthogonal. If I were parallel, what angle would I be if I am parallel to each other? 0 or 180. If you're 0, they're both going in the same direction. If they're 180, they're both going in opposite directions. It's like they're facing each other. Okay, that's an important concept for today. They're parallel. Okay, we could also talk about being perpendicular. Okay, I'm just playing. I'm not talking about perpendicular because that's not what we're using. It's orthogonal. What angle is different between the two of you are orthogonal? What's the difference? 90 degrees. Talk with your neighbor real quick. How could you more easily, instead of just doing the whole formula, how can you tell if two angles or two vectors are parallel easily? And how can you tell if two vectors are orthogonal pretty easily? Talk with each other. All right. As we're looking at this thing, Henry, how can you tell if two angles are parallel or two vectors are parallel easily? Not quite there. Anybody remember how we can easily tell that, Megan? Yeah, so remember, like, we talked about this. If it was like some number, okay, and you could multiply them together and then they would be equal, that's when we could tell we're parallel. We did something like that where the dot products were similar. You're not wrong with that capacity. Okay, just a little bit different. But if we could multiply by something. And so the easiest way to determine that is like looking at this and trying to find the smaller of the two. Can you tell which vector is smaller out of the two? Then it's not parallel. Okay, like if I were to take this one, what would I have to multiply 2 by to get 3? Well, it'd be 3 halves. And if I multiplied 5 by 3 halves, that's definitely not getting me -1. All right, so you can't just multiply it by something. Okay, that's how we can tell if it's parallel. How could we tell if two things were orthogonal or not? Dot product 0. If you're dot product 0, then they are orthogonal to each other and you don't have to do any other work. Everybody good with those concepts? All right, based on the fact that today is a pretty straightforward lesson, we're going to do a bell work part 2. Okay, so just a good application of what we're doing. I know you don't love story problems, so just making you think a little bit more is good for you. Okay, read through that one with your neighbor, see if you can answer it. Go. So an interesting problem, a little bit different than other ones we've done. If he is floating freely in outer space, obviously we're trying to take away gravity for the most part and other things like wind resistance. The gravitational forces pulling on her body are negligible except for the forces of a nearby asteroid, a planet, and a star. Okay, so here's our setup. This is Iffy right here. She's being pulled in 3 directions. Okay, that way towards an asteroid, that way towards a star, and that way towards a planet. Based on that, she's going to move. We're not moving up and down. We all lie in the same plane. All we're doing is moving in 2-dimensional space. All right. If these are the forces, so this is the angle and the strength of each vector, point, which direction do you think Iffy is going to end up? Point, which way do you think she's going to end up? So looking out, we're getting angles of, you guys kind of had anything from here to like there, somewhere in this ballpark. But somewhat agree with that? We got to be a little bit more specific than that, but based off of what's happening, this one's pulling her left, but it's not pulling very much. These two are pulling her right. We're assuming it's going right. This one's down. That one, we got to balance it out. Everybody good? All right. So for us to figure out which angle she's actually going to be pulled at, we've got to figure out what happens when we put these 3 forces together. So we are literally going to put those 3 forces together. We are going to add them up and create a new vector. What do I need to do with my x values if I want to know the x value working on Iffy? Add them up. If we're trying to figure out the force, we're just adding them up. Okay, so we're taking 2 plus -1 plus 8. I get 9. Then I got to find my y's. So 4, -3, -2. I add those all up. I get -1. That's the new vector. That's the resulting vector when I put those 3 things together. So 1, 2, 3, 4, 5, 6, 7, 8, 9, -1. This is the new vector. So is she being pulled at 0 degrees or less than 0 degrees? Or less, because this is 0 right here. Okay, so she's being pulled down a little bit more, which would make sense. This is a pretty strong vector in terms that it's pretty long, and this one is definitely pulling her more down. That one's pulling her up, but maybe not as much as the others. Does that make sense why she's going that direction? This is our new vector, 9, -1. We want to know the magnitude of the net gravitational forces acting on her. So how do I find magnitude given those 2 things? Pythagorean theorem. Boom, we get 82, but you got to find the square root. So square root of 82 newtons is the force working on Iffy. Then we want to find the direction. Now this isn't what we did in bell work. In bell work we had 2 vectors and we found the difference between them. Here I've got 1 vector and I want to know the angle of that vector. How do I find that? Tangent. Yeah, good. Tangent of theta. Okay. Tangent of theta. If I want to know the angle, I'm doing tangent of theta. What's tangent of theta going to be equal to? -1/9. Y over x. That's my setup. How am I going to figure out what theta is? Inverse tangent. So in my calculator, all I need to do now is inverse tangent. Okay, so in my calculator, make sure I'm in degrees. I'm going second tangent, and then negative 1 over 9. I type it in. I hit enter. I get that. Negative 6.340 degrees. Does that look like a negative 6 degree angle? Yeah, that should make sense. And our newtons were 82 newtons, so a little bit more than 9. Yeah, that line looks a little bit more than 9 based on our values there. Questions with how we set that thing up? Just a little bit different, but it's applying exactly what we know to a new situation. We just want to make sure we got that. Everybody good so far? All right, let's jump into notes. We're just doing one page of notes. The back side is what we're going to do tomorrow for notes. So today we're just working on the front side only. 2 problems. We hate story problems when we look at them, but don't be distracted by them. Okay, they're not that difficult. Let's talk about work. I'm going to do a visual demonstration so you at home, you don't get it. You guys just missed out on a great demonstration. It was wonderful. Jack, you especially, you would have really appreciated it. All right, here we go. The work done in moving an object from point A to point B with a constant force vector of F is defined by this. Okay, so the work being done, you take your force vector and your movement vector. AB is going to be basically how far did your object move. Okay, work is commonly going to be measured in foot-pounds or Newton meters, otherwise known as joules. If you want to know more, YouTube that. Okay, it'll be very wonderful and teach you more. Okay. We're just going to worry about the math today. A girl pulling a wagon with a force of 50 pounds. How much work is being done when she moves the wagon 100 feet if the handle makes an angle of 30 degrees with the ground? All right, so she is pulling on this wagon. It's a 30-degree angle. She's pulling with 50 pounds of force. Is that the most efficient way for her to pull this wagon? No, because if you're pulling at 30 degrees, you are wasting some of your energy by pulling it up. Okay, if we were to just pull straight out, it would be more efficient. Now, it would be awkward because you'd have to be like laying on the ground pulling it. Not a great plan. Okay, so sometimes you want to waste some work that's being done. All right, so to find that, we're going to do work equals force times the movement vector. Let's do the movement vector first, so AB. That's how much we move the wagon. We want to write this as a vector because we're trying to find a dot product here. Anybody know what my movement vector would look like for this problem? How much did we move the wagon left and right? How much? 100. Did we move the wagon up and down? No. So it's 0. Don't let that be hard. It's pretty straightforward. I moved it left and right 100. I didn't move it up and down, so it's 100, 0. That is my AB. That is my movement vector. The other thing we have to do is find our force vector. What 2 things did they tell me about my force? 50 pounds and 30 degrees. That's not written in the vector form. Okay? We want to have a vector form where it's nice and clean inside of these pointy brackets. But instead what we know is a magnitude and an angle. Okay? We pulled with 50 pounds of force. So remember when we write this, you throw that 50 out in front. And then what would need to be written inside of these brackets? If I want to know how much I pulled left and right. Good. Cosine of 30, because I'm pulling it on the x-axis 30, and I'm pulling it on the y-axis sine of 30. Everybody good to that point? This is kind of awkward. We would rather rewrite this thing in the normal form. So boom, boom. What would I need to do with this 50? Distribute. So I'm going to distribute. So it's going to be 50 times cosine of 30. We don't necessarily need to use a calculator at this point. We can do this without it. What is cosine of 30 going to get me? Radical 3 over 2. And then I'm taking 50 times sine of 30. What's sine of 30 going to get me? A half. So what's 50 times a half? 25. And obviously here you could take 50 divided by 2 and be like, oh yeah, that's 25. Radical 3, 25. You could go decimal if you really wanted to, but it's going to be easier just leave it as radicals. One less thing to mess with later. Everybody go with me to there? To calculate the work, We then need to take our force times our AB vector. This vector times that vector, and we are doing dot products to figure that out. Talk with your neighbor, find the dot product. Go. Here we go. We are finding the dot product. So if I'm finding dot product here, Kara, what'd you do? Yep, multiply the two x's. So she is taking 100 times 25 radical 3. Then what else did you have to do? Yep, then we multiply the two y's, 25 times 0. Yes, if you're good at this, you would be able to see that pretty early on. I'm fine with you doing that. I just want us to understand how this connects to dot products. Okay, these two things are going to cancel. This is my answer, but obviously we could get a numerical value for that. 100 times 25 root 3. We hit enter. 4330.127. That's how much work was being done. What is that? Foot pounds? Foot pounds. Again, a funky unit, but that's my answer here. That's how much work was being done. How could I have done more work? What would it have been better how could I have done more work with this process? Henry? That would have been 89.9 degrees. That would have been more work? If we want this number to be as big as possible, right? We want this number to be as big as possible. So 50 times what would make this as big as possible? 50 times 1 would make that as big as possible, right? So we want cosine to be as close to 1 as possible. If we did the other way, we're going to not do a whole lot of work at all. So we would want that value to be as close to 0 degrees as possible. It's the most efficient use of force. Does that make sense? All right, let's look at the next one. How much work is done in moving a cabinet 20 feet with a force of 140 pounds applies at an angle of 40 degrees? So this guy's pushing at a 40-degree angle upward. That seems kind of silly, but try to figure out how much work he's being done. Go ahead and set that up. Work equals force times the movement vector. Figure out what your movement vector is. Figure out what your force vector is. Get an answer. Go ahead. Let's see what we can do here. We're starting out with AB, that movement vector. Brooklyn, what do you say here for that movement vector? Good. 20, 0. She moved 20 feet to the right, but we didn't move up and down at all. As much as you want to push that thing up, you're not that strong. So we got 20, 0. Then we got to find our force vector. But again, we're given angle and a force here, a magnitude. So Sam, what'd you write here in front of your bracket? 140, because that's the force that he's pushing up on that thing. And then what do you put inside the brackets? Cosine of 40 and then sine of 40, because this will tell him the x value. That will tell him his y value of our movement. Again, we are taking this, we're distributing. Okay, so I'm just going to leave it pretty easy and go 140 cosine of 40 and then 140 sine of 40. Yeah. Then we are finding the dot product. Our job here in the end is to find force times AB. I'm taking the two x values, I'm multiplying them together. So 20 times 140 cosine of 40. So 20 times 140 cosine of 40. And then we're going to multiply the two y's together. So 0 times that guy. What's that going to get me? 0, because it's times 0. And so my answer to this question is that. We can type that into our calculator to see what we get. But you type it in, you make sure you're in degrees. You get 2,144.924 foot-pounds. Questions? We did some work, and although that seems like a lot, it's a weird number that doesn't have a lot of meaning, but it would be more efficient. He would do more work if he didn't just push up at a weird angle. Okay, he could do the same amount of work that he did here, but push a lot less hard if he just changed his angle instead of pushing up at a 40-degree angle. Wonderful.